All right, so the topic we are going to cover in today's lecture is method to solve boundary value problems. The name of the method is the shooting method. So, can you see my screen?
Yes, sir.
All right, so the name is interesting. By the time I'm done with my lecture, I will be able to explain why this interesting name. As I said already, today's lecture will be brief, actually, at least I hope so. As I said, it's a method that we use to solve boundary value problems numerically. So just like in our last class, we have seen two different versions of finite difference method for solving boundary value problems. One for linear boundary value problems and the other one for nonlinear ones, right? Similarly, we are going to start with linear boundary value problem to the version of shooting method that is used to solve linear boundary value problems. And you can see a linear second order boundary value problem here. The underlying equation is a differential equation second order. And we need to solve the equation numerically in this interval where at the points A and B, the values are given alpha and beta. Now, what shooting method does is splits the original differential equation, splits the original boundary value problem into two different problems, both of which are initial value problems. So you have one boundary value problem, you split it into two different initial value problems. Both of these are initial value problems. As you can see, in the first initial value problem, the differential equation remains same. Of course, the interval remains same. But the initial conditions are given only at the point x equals to a and not at b. And the first condition is the exact same condition given in the original problem, but this one is new. The derivative of y is given at a equal to 0. And the second differential equation looks a little different, right? There is no r of x involved. And here we can see that both of the conditions are new here. And technically, this initial condition does not agree with the one given in our boundary conditions of the original problem, right? So what happens is, if you solve these two problems, and if you get, for example, the solution of this equation, if you found it to be some function y1 of x, and if you solve the second problem, and if you get the solution to be y2 of x, of course, a solution, then using this y1 and y2, you can find the solution to the original boundary value problem using this formula. Now, why does this work? Let me explain. Basically, please let me share the whiteboard. The first initial value problem is y double prime x plus px y prime x plus qx y plus rx equals to 0. And the second one is almost similar. Oh no, it's not exactly this one, but we have an equal sign here, and there is no equal to 0 there. And the second initial value problem is y double prime x equals to p of x y prime x plus q of x y. And there is of x here, you can understand that. Okay. Now, the initial conditions for the first initial value problem is y at a is alpha, just as given in the original boundary condition. and y prime at a is 0, right? And for the second initial value problem, y at a is given to be 0 and y prime at a is equal to 1. Now, now, if this equation, the first equation is satisfied by y equals to y1, then you can understand that you can just replace y by y1 in the first equation. And the second solution, we assume that the solution of the second initial value problem is y2 of x. So you can just replace y by y2 in the second equation. So y1 of alpha a is alpha, y1 prime a is 0, y2 a is 0, y2 prime a is 1. Now, let me get back to the PDF momentarily. You can see the formula given at the end is yx equals to y1x plus beta minus y1b by y2b into y2x, kind of a linear combination of y1 and y2, right? So let me write that equation here again. The final formula is yx equals to y1x plus beta minus y1a by y2a by 2x. Let me recheck second time. I did a couple of mistakes actually. So it should be B here and here and not A, which makes sense, which will make sense eventually. Okay. Now, if you differentiate twice, then what you get is, I'm explaining why this works. Why this formula works. Why this y of x is a solution to the original boundary value problem, where in the expression of yx, you have two functions y1 and y2, who were solutions to unknown. So far, they are unknown to us. They are not. They look similar to the given boundary value problem, but they are not exactly the given boundary value problem. So they are so far unknown to us. So these y1 and y2 are solutions to these two unknown initial value problems, and somehow the function this particular linear combination of those two guys, as I claimed, is the solution to the original boundary value problem. I'm trying to prove why. I'm trying to prove why. So if you differentiate this yx twice, you get y1 double prime x, and this is a constant, y2 double prime x. So what I'm going to do now is replace y1 prime x here by the right hand side this, because this is y1 prime x, right? And we are going to do similar for y2 double prime here as well. So in the next page, I'm going to write y1 double prime x equals to, first, the right hand side was p of x. The format is px y qx, px y prime qx y rx. So let's just follow that. So px y1 double prime x, not really, y1 prime x plus qx y1x plus rx plus that constant, which was beta minus y, beta minus y1b by y2b. So beta minus y1b by y2b times the similar looking expression for y2 double prime. So p of x y1 y2 prime x plus q of x y2x, and we stop here. So you can see that I have just replaced y1 double prime and y2 double prime by the two right hand sides here. So if you simplify the now and just try to find where we have p of x and take that as common, you get y1 prime x plus beta minus y1 b by y2 b y2 prime x. We are done with p of x plus. Now let's deal with q of x. So we have y1 x here, and we have beta minus y1b by y2b times y2x here. And we are also done with q of x. All that remains is a single r of x from here. Now, as you can see, you can clearly see that this is the exact expression of yx in the formula. So the coefficient of q of x is here simply y of x. And this guy is just the derivative of that function. So this is just p of x times y prime x. And at the end, we have an r of x. So you can see that on the left-hand side, we had y double prime x. So this is the differential equation in the boundary value problem. So this y indeed satisfies that equation, right? So all that remains is checking whether this y also satisfies the given boundary conditions. So the boundary condition, we can take that very briefly here. Won't take much time. So the boundary condition, the first boundary condition is y at a should be alpha, right? So let us check whether that y at a should be alpha. Let's see what we get. The expression for yx is this one, right? So let us check here actually. Y at a is simply y1 at a plus beta minus y1b by y2b, y2 at a. Now, from here, you can see that y1 of a is just alpha and y2 of a is 0. So this guy is actually 0 and this guy is actually alpha. So we have verified that y of a is indeed alpha. And what about y of b? Let's write here. I'm sorry, the writing is not sequential, but I'm just trying to make use of the space here. So y at b should be y1 at b minus beta minus y1b by y2b times y2b. Just following this formula again. So y2b gets cancelled out. So we have y1b. Oh, I think I wrote minus here, it should be plus. So plus beta minus y1b. The two y1b gets cancelled and all that remains is beta as we were expecting. So somehow this is working, right? So what we originally had is a boundary value problem with two boundary conditions at the two given points. We introduced two initial value problems with different conditions, of course, different initial conditions. And we collected the solutions of those two initial value problems. And we have a formula from which we can find the original solution yx. The formula is just a linear combination of those two solutions of the two initial value problems. So this is how we can make sure that this actually works. Even though it seemed very unlikely, it should have been appearing very unlike to a few of you at least. Now here is the algorithm for the linear shooting method. This is just declaring the input output variables, and that's all. So what we are doing actually in the method, instead of solving a boundary value problem, we are writing a code for solving initial value problems, just two initial value problems, that's all. So they did exactly that. They declared 8, B, A, N, and they found 8. And there should be two sets of initial conditions. That is why they introduced two variables v, u, and v with proper indices. And they used RK4 method for solving the two initial value problems. Now, what is the easiest method for solving initial value problem? I hope you remember that the first method we learned for solving initial value problem numerically was Euler method. So I want you, as the assignment for today's lecture, I want you to solve a boundary value problem that I'm going to provide after the lecture using linear shooting method. Of course, the boundary value problem is going to be a linear differential equation. Otherwise, you cannot use the linear shooting method, right? So you are going to use linear shooting method, but instead of RK4, to make things simpler, you are going to use Euler equation, Euler method to solve the two initial value problems. All they did, you can clearly see that they just solved two initial value problems simultaneously. It kind of works like as an assignment we have seen for Euler's method. I have provided you a, and generally Euler method works for single order equations, but I provided you I cannot remember if that was a second order differential equation or third order. I think it was a second order. So you had to assume a variable to make it convert into a system of two initial value problems. I hope you remember that. And you had to solve those two initial value problems simultaneously to get the final result. This one works like that as well, but you have to understand that here the original problem is also second order. So you have, while solving the two initial value problems, both of which are second order, you have to convert both of them into a system of, each a system of two first order differential equation, right? That is why they used two-dimensional indices here. And also they used two sets of those for two IVPs actually. So technically, linear shooting methods code is not a code for something new. It's just a code for solving first order system of first order differential initial value problems, and that's all. So please let me know if there is any confusion anywhere in the process or understanding the method. Okay, so let me continue and move on to nonlinear shooting method. So now, just like in our last class for nonlinear finite difference method, we have a differential equation of second order here, but on the right hand side, we have no specific structure, as it is going to contain nonlinearity. And the boundary conditions are just like before. Now, what we do in nonlinear shooting method is similar to the linear shooting method. We are going to solve initial value problems just like linear shooting method. All right. So even though this was actually, you can see the difference. Up to this point, this is same. But after that, here we had the value of y given at b. But here we are given the derivative of y at a, basically not given, we are assuming the derivative of y at a to be equal to some parameter t. The method works like this. assume a random initial choice for t. Let's call that the value of t naught. Then what we do is somehow we iteratively find better values for t, like t1, t2, t3, etc., so that this sequence of t converges to some value. I think it's a little blurred here, so let me zoom out a bit so that it appears comparatively clearer. So we shall construct a method to find better approximations for t, so that as t converges to some most suitable value, the value of y at b converges to beta. Now, how do we find such a method to construct such a sequence of ti? That's the question. Now, as I have said, we are going to start. Now, let me zoom a bit. As I have mentioned, we are going to start with some t naught at first. This is up to us, some random choice. What it physically means is we are given that y at a is alpha. Now, since we have chosen some random value of t naught as the slope, we are kind of shooting along that slope, just treating it like an initial value problem, just the way, for example, Euler method works. And maybe we are along that slope, we are going to get the basically, you know how the initial value numerical methods work for initial value problems. So initially you shoot along a slope, you then reach up to the next grid point, then you move along another slope, you get to the next grid point, and finally you get to the final x equals to b point and get a value of y. That's how it works, right? So the final value of y is not going to be equal to beta unless you are the luckiest man on earth, of course. So what happens is, this is some first approximation for y at b. Of course, it's not going to be perfect. Then the equation that we are going to use to find the next, basically, we are going to use Newton-Raphson method here. Let's see how. At the end, y at b for our best choice of t should be such that this guy equal to beta, so that this guy minus beta equal to 0. So this is the equation that we need t to satisfy, right? So technically, we are going to solve this equation for t, but this equation is very, it may contain very irregular terms, right? So most probably we are not going to be able to solve it exactly analytically, but we have numerical methods for that as well. So we are going to solve this equation using Newton's method. And this is the equation for, this is very well known to you, Newton-Raphson equation, right? There is another problem. We do not really have the derivative in our hand. So how to find the derivative of y with respect to t? To manage that, there is a mistake. It should be y prime here. I think the original Barden's book contains this mistake as well. So, so basically what we are doing is we are considering this boundary value initial value problem with the derivative of y at a assumed to be t. Then if you differentiate this equation on both sides, this equation differentiate on both sides with respect to t. Now you have to remember that in the original equation, the derivative was with respect to x. This prime means the derivative is being conducted with respect to x. It's not derivative with respect to t. What we did was we replaced y of x by y of xt everywhere in the original differential equation. That's all we did in this page. Now, differentiating both sides with respect to t partially, we get something like this. We just applied chain rule on the right hand side. It looks ugly, but it is not actually. We just applied chain rule, straightforward chain rule. Now, you should be able to understand that x and t are independent variables. So this del x by del t should be 0. So the equation gets a little further simplified and it looks better now, right? Now, what we are going to do on the next page, okay, these are the initial conditions also. We differentiated the initial conditions with respect to t as well to get this. And the original value of y at a was given to be alpha. Alpha is a constant, so we are differentiating with respect to t. So we are always going to get a 0 on the right hand side. But what about this one? We assumed that the derivative of y at a is t. So when we differentiated with respect to t, we got 1 on the right hand side for this initial condition. Now, what we did in this page is we considered this guy, not the entire guy, but only del y by del t to be z. So consider del y by del t to be z. So what happens is when you differentiate someone like del y prime by del t, which actually means del by del t of dy by dx. Since t and x are basically independent, we can just simply write d by dx del y by del t. We can swap the order to get this. This is simply y del y by this is simply z. So this is just dz by dx. And finally, we can just write z prime because by prime, we mean derivative with respect to x. So that's what happened here. The same idea just for y prime, y double prime. And if you rewrite after substitution, then everything is converted in terms of z, and we get an initial value problem like this. And here we should have z prime constant. So we have Euler method and RK4 method and other methods for solving initial value problems. If you solve this initial value problem, the solution you are going to get is the expression for the variable z. And if you solve them numerically, you are going to get numerical values for z at different points, right? But what was z? Z was time derivative. I mean, this is not exactly time, this is t. So t derivative of y, right? So can you recall in the Newton-Raphson equation that all of this started because we do not have the derivative of y with respect to t ready with us. This was the guy we were trying to find out. And this is exactly z calculated at b comma tk minus 1. So interestingly, just to find this derivative, or in other words, just to find z, you have to solve this initial value problem. The solution of this initial value problem is just z. So if you can manage that, then you have the denominator ready. So you can iteratively.
Sir,
yeah.
Will we have to solve this using Newton-Raphson method at every step?
Yes, exactly. That was
As in,
I was going to.
for the first step we will solve z, then again for the second step we will solve z again, and like that.
Exactly. To find a sequence of improved values of ti from ti minus 1, we have to solve for z. I mean, you have to solve the initial value problem in the last page in every loop. And at each loop, you will get a better approximation for ti. And using that ti at each loop, you are going to solve this initial value problem, but this time T1 instead of T0. Next time T2 instead of T1. And you have to continue the loop until you get the value of y to be sufficiently close to beta at the point x equals to b. After you reach that point, you stop the loop. This is how the algorithm works. So there is a lot of initial value problems involved. No boundary value problem involved. Now, this here is the you could basically use another method for the solving for t. For example, you could use secant method, another false position, and other methods you learned in numerical method course. That's also fine. But if I provide you any problem just for this course, I want you to follow or stick to this method that involves Newton-Raphson equation. Okay, but in your, I mean, if you ever use later in your life, if you ever use shooting nonlinear shooting method, you can choose any method you want to solve for t. Okay, here is the algorithm, and again, they are using RK4 method for solving the initial value problem, and I think the algorithm should be okay to you. You have to just solve the initial value problems in loop to get better approximation for Ti at each loop until y at b is sufficiently close to beta. Please let me know if there is any confusion involved.
Sorry, will it be okay if you could briefly recap? It's hard to keep track of how we're progressing.
Do you mean starting from the linear one, or do you mean only the non-linear one?
Just the nonlinear part, since there are several IVPs involved. I've lost track of
Okay.
where.
Okay. All right. Here is the recap, of course. This meeting is going to end abruptly, so I'm for stopping the meeting. Please rejoin. Here is the short recap of the whole process of nonlinear shooting method. You are given a differential, a boundary value problem that looks like this. What you are going to do is replace the condition that involves the point x equals to b by someone that looks like this. So we are basically converting the given boundary value problem into a single initial value problem. The problem now involves the derivative of y at a, and we are assuming the value of y prime to be initially some t naught. We are going to approximate a better value of t. We are going to improve t naught to another t1, basically using this equation. So because finally, eventually, our best t should satisfy this equation. If t is perfectly chosen, then it is going to be a perfect exact solution of this equation. So we are going to solve this equation for t, and the solution that uses Newton-Raphson method looks like this. So this equation can infinitely provide us, supply us infinitely many better approximations for TIs, right? But to find the derivative, we have to construct another initial value problem. After so many calculations, we got this initial value problem. So if you solve this initial value problem, the value of z is going to be replaced at the denominator. It is going to replace the derivative. So this is the final equation. So forget the Newton-Raphson equation. This is an iteration equation that we are just going to use to improve the value of Ti. And to find z, we are going to solve this initial value problem at each loop. And at each loop, we are going to solve this initial value problem to get y. Y at B, actually. The y at B that's sufficiently close to beta is the final one that we desire. Now, actually, this kind of geometrically, it looks like this, that at x equals to a, the value of y is exactly alpha. At x equals to b, you want the y to be exactly beta. But what we are going to do is we are choosing some t naught as an initial guess of slope, guess for slope at x equals to a, and using that slope, we're going to get some approximate curve that's not going to hit beta at exactly beta at b, right? So this is probably for t naught. Then using that iteration equation, you are going to get a t1 and use that t1 to solve again the initial value problem to get something like this. Using this t1, you get t2 using the iteration equation, and starting with that, you get something like this. So what we are doing is kind of shooting our curve using better and better values of ti and hoping that it hits beta, or at least close enough, a point that is close enough to beta. That's what we are doing, hence the name shooting method. So is the confusion clear, or is the recap helpful, Ilham?
Sir, so here is beta the value for y at b.
Yes, which was
So
the
we
given
want,
boundary condition.
so and we want to choose t such that the value of y at b minus beta is 0.
Y at b minus beta as 0, yes. But then again, our equation now involves a new parameter. That is why we're writing a t here. You are going to get different y at b for different t. So t is a new parameter now. Just like this drawing, if you start with different values of t, you are going to end up at different values of yb, right?
Sir, but the original equation was not a function of t. So how are we using t as a parameter inside the equation?
Basically, you are not getting a function for y, b, comma, t. What you are actually solving the original the first initial value problem, the initial value problem we first proposed. You are going to solve that one, this one.
So for each t, we are getting a new IVP. That's what we mean.
Yes, after the end of each loop, you are going to get a new y at b. And each loop has different t, right? That's what's happening.
Yes, I think it is clear now.
All right. All right. Any more questions from anyone else? All right. So within an hour, I'm going to post a new assignment. The assignment is going to be on linear shooting method, not non-linear. And my specific instruction is you have to use Euler's method to solve the IVPs, not RK4 method, which is given in the original pseudocode or algorithm. I'm going to write that special instruction in the assignment problem as well. So I think if that's all, then we can end the meeting. So let me stop the recording.